Hello, my people. Hope we're doing well. Now, like I said, what does all this mechanics mean for application of vector function integration? We're going to look at two today. One is displacement, one is distance traveled. Now, remember that those have very specific meanings. Displacement simply means how far am I from where I started. So if you're looking for how far the terminal end of a vector is at time b than where it was at time a, you simply need to do the definite integral from a to b of each component and you get a vector. I mean, you basically get how far it moved in terms of its horizontal displacement, and you get a component that tells you how far it moved in terms of its vertical displacement. So displacement doesn't have anything to do with how you got there. Maybe you got there in a windy kind of way. It just measures the distance, okay? Distance according to x, distance according to y from where you are now from where you were at time A. When you're dealing with distance traveled, you are interested in the length of the route that you took to get there, okay? And notice that this basically looks like the formula for arc length, because it is, okay? Now, v1t is the x component, and it is of the velocity vector. So v1 of t squared is actually dx dt squared. That's what that is. v2, of course, is the y component, and of course, of the velocity vector, it is the derivative of the position vector, and that is equivalent to dy dt squared. So this right here is the arc length. So, you know, kind of a goofy example, but if we're thinking about the difference between displacement and distance traveled, let's use from here to San Antonio. If I ask how far San Antonio is on the map, or basically how far it is across the globe, straight shot, that is displacement. You draw a straight line from where you are to San Antonio, that's displacement. If you're actually planning a trip, however, you're going to be traveling a greater distance than just the simple distance in a straight line, because roads don't always go in a straight line to where you're headed, right? You kind of have to go a little bit out of your way. That is distance traveled. And so that makes sense that distance traveled would be our arc length, okay? All right, let's go ahead and let's do an example that deals with those. A particle moves in a plane with the velocity vector v of t is equal to t minus 3 pi cosine pi t and 2t minus pi sine pi t. And you're like, gosh, that's a whole lot of pi's. Well, if I'm going to be integrating them, those pi's are going to disappear because they're there as a result of the chain rule. And therefore, they're there to make sure that when I integrate or when I anti-differentiate, the pi that I put in the denominator cancels out with something. So let's go ahead, and if I need to find the position of the particle at t is equal to 4, what I need to do is I need to find the position vector. Now I can do that because I'm given the initial condition right here. And once I find it, basically what I need to do is I can well, let's go ahead and let's do it with displacement instead, okay? So let's say that I want to find how far the particle's placement at t is equal to 4 is from my original. So what I need to do is I need to basically solve for the displacement. So 0 to 4 of my x component of my velocity vector should give me the distance, or the displacement of the x component from 0 to 4. This integral from 0 to 4 of the y component should give me the total displacement in terms of the y measurement from 0 to 4. Okay, well, let's go ahead and do this. Neither of these is all that difficult. I know that when I integrate this one, it becomes t squared over 2 minus, or actually it's plus, actually no, it's minus, because cosine is the derivative of sine, right? And sine of pi t. Now that's the case because, remember, you would have to divide by pi when you're anti-differentiating, and that would cancel out with that pi. And I need to evaluate it from 0 to 4. Now, when I plug in 4, that's going to be 16 over 2, which is 8, minus 3 sine of 4 pi. And then I need to go ahead and do it with the 2. That's 0 minus 3 sine of 0. Now, here's the great thing. This, and this are all 0, and therefore my x displacement is simply just 8. All right, now this one becomes t squared. Now, sine is the derivative of negative cosine. So that negative cosine, that negative out in front of the cosine is going to unnegativize this negative, and we're going to get plus pi, the pi goes away, cosine pi t from 0 to 4. Okay, let's go ahead and plug in. I'm going to get 16 plus cosine of 4 pi, and then I'm going to get 0 plus cosine of 0. Now, 4 pi is, of course, coterminal with 0, so this right here is 1. This right here is 1. You're going to get 16 plus 1 minus 1, or just 16. Now, that means that my displacement vector basically tells me that from 0 to 4, the particle moved 8 positive units in terms of its horizontal, or its x displacement, and 16 units in terms of its vertical displacement, its y movement. If I take those and add them to my initial, I recognize the fact that I'm going to be at 921. And actually, it's a point, not a vector, sorry. So 921. And all that is basically this is where it started out, this is how far it moved, and you just add them together and get 921. Now, what is the total distance traveled by the particle from 0 to 4? Well, that winds up being a little bit nastier, right? Because we're going to be using our arc length. And these are not simple expressions, right? Neither of these is a simple expression. But if we do t minus 3 pi cosine pi t squared, and then 2t minus pi sine pi t squared dt, while that's really nasty, I can plug it into my calculator. Basically, you plug it into your calculator just like you would if you were dealing with a parametric. So let's go ahead and do that. All right, let's go t minus 3 pi cosine of pi t, and this one becomes 2t, yeah, they're both minus pi sine pi t, and then we'll go back to the main screen. Now, that means that if I just do the integral from 0 to 4, I simply need the square root of x1 squared and the sum of it with y1 squared. Make sure you put a t out here, and I press enter, and I'm left with, gosh, the suspense is killing me. Okay, well, I'll go ahead and spoil the surprise. It's 33.533, unless I made a keystroke error somewhere, which I don't believe I did. Ah, there we go. 33.533. Now, there will, of course, be some that you can do by hand, but even if you could do that one by hand, why in the world would you want to, right? There are just some that are just not worth it. All right, let's go ahead and take a look at one that is extremely similar. We're just going to do a couple of these just to sort of up our comfort level with these. Now this one, I have the velocity. I have the velocity vector, and I have the position of the particle at time t is equal to 0. That's what this is. Okay, this right here is r of 0. I need to find the position of the particle at time t is equal to 3. Well, the position at time t is equal to 3 is basically this plus the 2 plus the displacement along the x measurement along the horizontal, and 6 plus the displacement along the vertical. Alrighty, let's go ahead and do that. So we know that the vector for displacement is going to be 0 to 3 for 3t squared minus 2t dt, and then 0 to 3 of 1 plus cosine pi of t dt. Now, let's go ahead and do them, let's sort of separate them out. And we know that this first one is going to wind up being t cubed minus t squared, and I'm going to be evaluating from 0 to 3. That's going to be 3 cubed minus 3 squared, so it's going to be 27 minus 9, which is 18. So 27 minus 9 minus 0 minus 0, so that's going to be 18. Now this one winds up being t. Now notice that there's no pi out in front of the cosine pi t, so I actually, it's unfortunate, but I need 1 over pi cosine pi t from 0 to 3. Now the great thing is, is that they're basically going to, oh sorry, this is supposed to be sine. Sine. The great thing is that they're going to cancel out because the 1 over pi is not going to matter because sine of 3 pi and sine of 0 pi, or just 0, are both 0. And so I get 3 plus 1 over pi sine of 3 pi minus 0 plus 1 over pi sine of 0. That's 0, that's 0, that's 0, and I'm just left with 3. So the displacement vector is 18, 3. Now, that means that what I have here is 18, 2 plus 18, and 6 plus 3. My new position is 29. That is the answer to part A. Now, if I wanted the distance traveled, I would do the same thing that I did in the last one. It's basically arc length. So I have the arc length from 0 to 3, the square root of 3t squared minus 2t squared plus 1 plus cosine pi t squared dt. And I won't break out the calculator, but if you go ahead and just plug it into your calculator, it becomes 19.343. And you would, do it exactly the same way. Just plug, this into your x1, this into your y1, and then go back to the home screen and just use that shortened notational version of the integral for arc length, and there you go. Okay, one more. I just want to make sure that this is one of those things that is really sort of driven in to our long-term memory, and that's why we're doing 3 examples of it rather than just 2 or something. Alrighty, let's go ahead. And if we're going to, and it's actually asked exactly the same way, okay? The velocity of a particle moving in a plane is given, along with the position of the particle at time t is equal to 0. So again, this right here is my r of 0. So what I want to do is I want to find my displacement vector. My displacement vector is my 0 to 3 of e to the t minus t dt, and 0 to 3 of e to the t plus t dt. Now thankfully the anti-differentiation is going to be relatively simple in this one, and the first one it becomes e to the t minus 1/2 t squared, and we're going to evaluate from 0 to 3. And the second one becomes e to the t plus 1/2 t squared, and we're going to evaluate from 0 to 3. Now this becomes e cubed minus, and of course when you plug in right here, it's going to be t squared is going to be 9, so it winds up being 9/2 minus e to the 0 minus 0. Well, this, of course, is just 1. So if this is e cubed minus 9 halves, it's actually e cubed minus 11 halves. Okay, this, just like the last one, is going to be e cubed plus 9 halves minus e to the 0 minus 0, right? Because it's exactly the same, except it's plus rather than minus. This, again, is 1, and so it's going to be e cubed plus 7 halves. So what we have here is we have basically we need the 1 plus e cubed minus 11 halves and 1 plus e cubed plus 7 halves, and that's going to wind up being e cubed minus 9 halves and e cubed plus 9 halves. And that right there is the position of the particle at time t is equal to 3, because all I did was I took the displacement components of my displacement vector and simply added them to the ordered pair from r of 0, the initial position. Okay, and again, if we're asked for the total distance the particle traveled, it's arc length. Okay, and the thing is, I don't have to take the derivative. These are the derivatives, right? Because it's velocity, not position. And therefore, it is e to the t minus t squared, e to the t plus t squared dt. And if I plug, basically this into my x1 and this into my y1 in my calculator, and then I go to the main screen and I basically type in 0 to 3, of x1 squared plus y1 squared dt, what I'm going to get is 27.791, and that is the total distance. Okay, in the next video, I'm going to start doing some problems that basically are multi-part and basically bring to bear both the differentiation and integration aspects of bringing calculus to bear upon vector value functions. And so since you're watching this in class, just watch until the bell rings, and then the rest of it watch at home. Okay, but that will be video number 3, which will start shortly.